All right, I think I'm going to get started here. Looks like mostly everyone's back. All right, so good morning. I'm Jacob Burnim. I'm a graduate student here in the PAR lab. And today I'm going to talk about testing and debugging of parallel software. And for quickly some of my background, I've been working in the PAR lab for the past 3 years with Professor Kaushik Sen and the rest of the correctness and verification group on a number of different techniques and tools for helping programmers find and fix bugs in parallel software. And today, I'm going to both try to give an overview of, a high-level overview of kind of all of the work, all the recent work in this field, and talk about the tools we've developed here in the PAR lab in a little bit more detail. And I'll try to keep a mix of both kind of some of the theory and principles behind why these tools work, and also point you to a lot of tools you can download right now and use to test parallel software you're writing. And please interrupt with questions. I'm going to make it more interesting for everybody here. Okay, so I think one point that's come up a number of times over this course is that parallel programming presents a number of new challenges to writing correct software. We have new kinds of bugs, data races, deadlocks, memory consistency errors. And as a result of these bugs and other issues, it's much more difficult to test parallel software than it is sequential software. And when we find errors, it's also more difficult to reproduce them and to fix them. And really, the key to this difficulty is non-determinism. Right? The potential for, when your program is using multiple threads, the order in which their operations happen from run to run can change. And this can, if you have certain kinds of parallel bugs, then on some runs your program will be correct. But on certain runs, maybe very rare runs, you'll get errors. These errors can be very hard to find. So just talk a little bit right about, again, how this affects the testing process. Right? So for sequential programs, where we have a lot of experience testing those, and we typically expect that every time we take some input, that every time we run the program on that input, we should get the same output. So here, we run in the same parameters, we'll always render the same fractal here. And it's typically not that hard to get this kind of determinism in sequential code. But now in parallel code, because the different threads that are performing the work, they can be scheduled differently on different runs. It may be so we run it once, the threads go one way, and we get this image. And hopefully every different schedule that we run will get the same image. But if we have certain kinds of bugs, say maybe there's a work queue storing which pieces of the image we need to render, and we don't properly protect that queue, then there may be certain schedules where we'll get a different result. We'll get the wrong answer. Okay. And again, so this is kind of notorious that it's known that some of these bugs can happen only under very rare schedules, maybe 1 in 1,000, 1 in 10,000 runs. And also, which schedules you see when you run the program can be very dependent on kind of the configuration you're using, on what operating system you're running under, on the hardware. And worse, many of these bugs sometimes will disappear when you turn on debugging or logging code. So sometimes these are called Heisenbugs. Sort of trying to observe them makes them go away. Whereas having people report from the field, bugs, they have a test case, a parallel unit test, and it fails once every 2 months. So how do you ever fix a bug like that? And again, so we have this story for sequential programs. You create several test inputs. You run these inputs, you check the output, or at least you make sure the program doesn't crash. And I'd say we have a pretty good intuition for kind of how do you select kind of good inputs to test, kind of normal inputs and also edge cases, and also some intuition about kind of how confident we can be that our program works if we've run a bunch of different tests. But for parallel programs, we lose a lot of these properties. So now when you run a test, you only get a single possible schedule of the parallel threads. And it's not clear, how can we, how do you test many different schedules to see if, maybe there's a bug under some of those but not under others? And, even if you run your test thousands of times, how confident can you be that your code's really correct and that there's not some concurrency bug kind of hiding there that you'll find the next time you run the program? So I talked a bit about kind of what the challenges are here for this parallel testing. And I'm going to go through, we're going to talk about kind of three kind of high-level approaches for ways to find bugs in parallel programs. I'm going to start with kind of some of the oldest and simplest methods, these are just strategies for kind of generating random schedules, or just generating more schedules so that you at least get a little bit better coverage when you run your tests. And then moving on to more sophisticated techniques for trying to, maybe you run your program and you analyze the execution very carefully to see if you can maybe infer that there are bugs, that there would be bugs on other schedules. And finally, I'm going to talk about a technique called active random testing that we've developed here in the PAR lab that in some ways kind of combines the benefits of both these approaches and that we've had a lot of success with. And in all these cases, I'll point you to tools that you can download and use kind of on your code now if you want to try these techniques. Okay. Again, here's our key challenge. If we have a parallel program, and I'll imagine we've written some tests for it, although of course even writing tests can be very hard, generating inputs with known good outputs. Now the question is, so now what do we do now that this is a parallel program? So the simplest thing you could think of is maybe you should just run the program many times. If you have a lot of computers, you could run it thousands, hundreds of thousands of times, and just kind of hope for the best. See if you ever get a different answer. And the problem is often you really don't get that much randomness when you run these schedules. If you're relying on the OS scheduler and if you're running these all with kind of the same parameters on the same hardware, you may be really wasting a lot of effort. You might actually see only kind of a small number of really distinct schedules and be missing this huge space of other behaviors the program could have. And in particular, because some schedules are much more common on some hardware or some configurations than others. So we'd really like a way to simulate some of that, to get the effect, to find a way to generate more schedules we can test. And you might recall one of the easy parameters that you can change, something like the load on the machine. Okay, so this gets to one of the kind of earliest kind of effective ideas for testing parallel programs is called stress testing. Probably a lot of people have used this. And the idea is basically if you want to see more interesting thread schedules when you test your code, you should try something like oversubscribing the machine. If normally, on your 4-core system or your n-core system, you'd run with n threads, try doubling or quadrupling the number. So now a lot of the threads have to pause and are context switched, lose the cores they're running on. Or you could run several instances of the program at the same time. What other things people try, you increase the size, maybe if you're using some kind of cache blocking, you could purposely increase the size of your blocks, so now you get really bad cache behavior. And these are all just effects. The effect of all these is you just want to change the timing of the threads. The hope being that some schedules that you weren't seeing before, now your threads are pausing and context switching at kind of unusual places, and maybe that's uncovering wrong behavior. Well, this is a very simple idea. Right? So if you have a running parallel program, this is very easy to implement. And amazingly, this actually often works. So often when you do this, you immediately find new bugs. Although it can be quite hard to reproduce those bugs, as we said. And then another similar idea, something called noise making or random scheduling. Again, it's the same idea, just kind of throw, kind of an ad hoc technique at the problem, but just try to see some new schedules. You can do things like just add random sleeps or yields to places in your program. So particularly if there's some part of it you're kind of concerned about the concurrency or the communication there, you can just focus on that. And of course, there are tools that do this automatically. And they have a variety of different techniques to kind of seize control of the scheduling of your program. And then they'll themselves insert, context switches where your program, under normal operation, would very rarely context switch there. So again, it's a new way to see kind of new schedules. Let's see. And in fact, there are a lot of tools that you can download to do this. And in fact, what's interesting is it turns out that kind of the way you randomize the schedules makes a big difference in terms of how quickly you find bugs and what kind of bugs you find. So there are a lot of different kind of heuristics people use. So there's this tool from IBM called Contest, which is kind of noise making that's putting in these random delays. Then our tools, kind of Thrill and CalFuzzer, which I'll talk about much more later, they have a mode where they can perform this. and actually some very recent work from Microsoft. There's this probabilistic scheduler called CUZ, which is very clever about the way it randomly schedules your program. So it can actually provide guarantees about kind of how likely it is to find bugs, and form kind of nice lower bounds, and how many times you'll have to run the procedure to find certain classes of easy bugs. And another nice thing about these tools is a lot of them can provide replay. Right? Because they kind of take control of the scheduler, you have this property that if you kind of rerun them with the same random number seed, you'll get the same execution. So now if you find a bug, you can rerun that execution maybe in the debugger, and you can see kind of exactly what happened. So it helps debug the problem. Okay. So again, these techniques actually, although they're quite simple, can be surprisingly effective in practice. But there are some limitations. So you can imagine, in fact, the space of kind of possible thread schedules for a parallel program is enormous. It's something like exponential in kind of the number of operations each thread does, because of all the different ways those operations can be interleaved. So you could think, maybe if you just repeatedly run the program, you're likely to expose a very small part of this space. And again, if you do stress testing, with some different configurations, maybe you'll hit some other parts of the space, but typically still pretty narrow regions. And you can think random scheduling is kind of nice because now you can maybe explore some interesting schedules from all over this space of possible interleavings. But again, you can see that the vast majority of schedules you're never going to be able to execute. So one natural question is, we'd really like to be able to find errors in these programs without explicitly having to test a schedule in which an error occurs. Right, so is there some way that we can run some kind of test and learn something not just about the one schedule we ran, but about a large class of schedules, maybe all the kind of similar looking schedules the program has. Yeah, and in fact, that's something there's been a lot of work on, and that moves into kind of these tools for detecting and predicting kind of parallel bugs. Okay, so again, the question we have here is, so we observe a test run of a parallel program, and it doesn't kind of obviously fail. But it doesn't crash, and the output looks okay. I mean, maybe we're not sure that it's totally correct, but at least it doesn't look absurd. So normally we might just have to say, well, that test passed, and we'll have to move on to other tests. But we want to ask, well, maybe if we look at this execution, right, we could learn something more about possible bugs in the program. So the idea is here we have this program, you run it, and we'll say it produces, we can record the trace of the program. Right? This will be a log of every operation performed by every thread, right? Every read of shared memory or write of shared memory, every lock acquire and lock release, or barrier synchronization, and the order in which they all occur. And then we'll run a tool on that trace. And there are kind of two classes of tools here. One we could say is a detector of a parallel bug. So for example, for the one kind of parallel bug is a data race. So one of these tools, a race detector, will look just at that trace, and it will say, was there a data race on this execution? Because, of course, it's possible that a data race occurred, but in this particular one, it didn't propagate to the output. But we'd probably still like to know, or it's probably a pretty bad sign that there was a data race, and we'd like to report that to the user. And then even better, we can maybe look at that execution, and we could say not just on this execution, but on a similar one, could there have been a data race? Or could there have been a deadlock or some other kind of bug? Right, in fact, this technique's been generalized to a number of kinds of bugs, so data races, atomicity violations, which we'll talk about in a little bit, deadlocks, and also these kind of consistency errors that you can get when you're kind of you're not programming for the right memory consistency model your language and hardware is providing. Okay, so just recall, I think you've probably seen this a couple of times. I'll go over again. So a data race occurs when two threads kind of concurrently access the same memory location. So access it at the same time, and at least one of them is a write. So in this case, just a very simple program here, but just to increment this variable x twice. But there's a data race here, which there are several. So these two writes to x and the two threads are not synchronized. So they can so what can happen is these can run at the same time. And so both threads will read the initial value of 0, and then they'll both write 1 to x. And you'll lose one of the updates. So you'll end up with the final value being 1 when it should be 2. And data races are a very common error. And this is kind of a simple example. But we find when we test, for example, large Java applications, we typically find many, many data races in them, often leading to serious bugs or to serious, incorrect program behavior. So there's been, kind of 20 plus years of research on race detection. I'll just briefly kind of describe some of the main approaches here. Got to be back at the end of the 80s. This happens before race detection, right? And this is a technique for detecting. So it looks at the trace and it really just asks, whenever you see two accesses to a variable and at least one of them is a write, is there an intervening synchronization between those two threads? Right? And if there's not, then those two statements could happen kind of right next to each other in time, and that's a data race. So this technique is nice because it has no false warnings, but we might want to predict races that happen not just on the execution we saw, but on other executions. So also someone proposed something called lock-set race prediction. And this is kind of a formalization of this notion that just roughly whenever you access a variable, or if you look at all the accesses to one variable in a program, there should be some common lock held across all of those accesses. Right, and that should be the lock that's protecting that variable. So lock-set race prediction looks to see if you ever violate kind of that programming discipline. And if you do, it can produce an error. Or it can, make a warning and report that to the user. This is nice, this is very efficient, but you can see it can have a lot of false warnings. And I'll show an example of that in a second. And most recently, a technique now that a lot of tools use is called hybrid race prediction, which kind of combines the best of both of these techniques to give you kind of fewer false warnings than lock-set, but still most of the performance. Okay. And again, so let me define these terms I've been using. Right? So a false warning, we'd say, is when the tool tells you, it found a bug in your code. For example, it found a data race. But in fact, that race can never happen in a real run. And there's really a trade-off here between the amount of coverage we get, right, when you run the tool, how many real errors you find, and how many false warnings the tool will also give. So this hybrid race prediction, right, generally has better coverage, so it'll find more bugs than happens before race detection, but it will also give you false bug reports. And sometimes you have to just run two different types of tools and see, do you have so many false reports that it's not worth it to go through them all, or is the number small enough that it's worth your time to check all of them to find the real bugs? And just to show you kind of a quick example here, to show you kind of what these techniques work like, or how these techniques work. So imagine here we have kind of one trace of a simple program. So one thread writes to X, and then holding a lock, it writes to Y. And then another thread runs. While holding a lock, it writes to Y, and then it has a read of X. And so the program is written such that if X happens to be 0, a real program error will occur. So you can see kind of it happens before race detector. It will say, well, between this write of X and this read of X, there's a synchronization event. Right? The unlock from one thread kind of synchronizes with the lock from another thread. So it won't report that a data race happened. And so if it happens before race detection, to report this race, there actually has to be an execution in which, kind of thread 2 runs first. So there's no lock acquires and releases between those two operations. All right, on the other hand, a lock-set or hybrid race predictor, it can just see, well, you're not holding any lock when you write to X, and you're not holding any lock when you read from X, so it can just say that looks like a data race to me. And in this case, it'll be right. That is really a race in the program, and in fact, it's a real program error. But on the other hand, if we modify this program slightly, so now the write to X is still outside of a lock, but now the read of X is inside of the lock, and it happens only if the read of Y in thread 2 is 1. So you can see that, in fact, this program does not have a data race, because the only way this kind of Y can be 1 in thread 2 is if the first thread has kind of run completely and released the lock, in which case, X will never be 0. Well, so we can say there's a data race here, but it's not kind of, I guess there's a data race, but it's sort of not a bug. And again, you can see that the write that happens before race detector will report an erase. And the lock-set or hybrid one will. And actually, I'm calling this a false warning, although that's a little debatable, because in this case, there is really, oh no, I'm sorry, this is really a false warning, right? Because if you try to run that read at the same time as the write, so you run thread 2 first, then Y will be 0, so in fact, the read is never executed. So this kind of looks like a data race, but you can see there's actually no way you can run this program so that that read kind of happens concurrently with the write. Okay. So I'll just quickly list, right, so there are a number of tools that implement this kind of race detection. So we heard yesterday about Intel Thread Checker, which I believe happens before race detection for code written with kind of C and P threads, or also any kind of C or C++ based code that uses a synchronization library built on top of P threads, like TBB or OpenMP. There are also a number of tools based on kind of Valgrind, and both of these tools kind of they dynamically instrument your binary as it's running to kind of capture all of the reads and writes that the code performs. There's a tool from Microsoft called Chess for managed code. It's actually really more of a model checker, but it does perform race detection. And of course, our tools from Berkeley that are active random testing tools I'll talk about later, they also implement hybrid race detection. We have CalFuzzer for Java and Thrill for C. I think I'm going to skip over these, but I'll just note that more recently there's also been work on kind of detection and prediction tools for atomicity bugs. And these are cases where you have some block of code, like here a deposit to this bank account, that you want to happen kind of all at once. So it shouldn't be possible to kind of, what we're saying is in any run here, so this little atomic, that's kind of an annotation saying, we believe we've implemented this so that whenever you run this, the effect is always as if it ran all at once, kind of without being interrupted. And in this case, this specification is false. This is not atomic, because of course if some other thread jumps in between the time when we, for some reason, release the lock of L and then reacquire it, for example, if two calls to deposit happen at the same time, we can lose one of the updates. But this is just to show that even if you have no data races, right, you can still have higher level concurrency or parallelism errors. Right here, all reads and write to balance are protected by a common lock, but in some sense the lock doesn't cover a wide enough region. Right, so this code is still not correct. And our tool CalFuzzer can predict atomicity bugs for Java. And there's actually a large body of research on detecting and predicting atomicity violations, but I'm not aware of any other publicly available tools. And again, we can also predict deadlocks for Java. Cases where, say here, thread 1 acquires lock L1 first, thread 2 acquires lock L2 first, and then they each go to acquire the other lock and the program will hang. And I guess I'll just briefly point you to, so I've been talking about dynamic analyses. These are tools that work by running your program and then either kind of attaching to the program and observing it as it runs, or somehow generating a trace and looking at the trace later. There are also tools that perform static analysis. So these just examine the source code of your program and never actually run it. And this can be useful, for example, if you want to test a piece of code that isn't actually in a complete program. So you can start testing the code before you're even able to run it. And again, there's been much work on statically finding data races, deadlocks, atomicity problems. And one kind of really effective tool for that, for Java at least, is called Chord, which is developed by Meyer Nyack at Intel, and our group has collaborated with him a little bit on that tool. Okay. So any questions before I move on? Great. Okay, so we've seen two different approaches to kind of testing parallel programs. Right here, by testing, we're talking about ways to find, either just to test the program on various schedules and see if we get wrong output, or ways to kind of examine runs of the program and see, do we see bad kind of parallel patterns, things like data races or deadlocks, or possible data races or deadlocks. But the problem is, if we said, random testing, it can be very effective, but it can miss a lot of bugs because it can only look at a very small part of the program space. And predictive analyses, they, again, can be very effective. They can find a lot of bugs, but they have this problem of false warnings. And if there are only a couple of false warnings, maybe that's all right. If you find 10 real bugs, it's okay if you waste a little bit of time on 2 false reports. But if you only find 2 real bugs and there are 100 false reports, now it might feel like it's not really worth it to use the tool anymore. So what we'd really like is some way to kind of combine these two. To use predictive analysis to find places where there might be a parallelism bug, but then somehow to use random testing, maybe to some kind of biased random scheduling, to see if we can actually create each bug. So that instead of just telling the user, here are possible bugs in your program, we can say, we found we believe there's a data race, and here's a real execution where that data race happens. Give the programmer an execution or a trace that they can debug. Okay. And that's the key idea in active random testing. So again, just to kind of show a graphical example here for data races. The idea is, we take the program, we maybe run it several times with some kind of predictive data race or some kind of data race predictor. And that would give us a list of potential data races. There's something here, maybe it's possible for the read at line 14 to race with the write at line 19, or the write at line 87 to race with the line at the write at line 92. So these are kind of reports that a program will give you. But then we might, and then normally the user then will just have to look and say for each of these, can the code at line 14 and line 19 really race? So what we'd like to do is instead of making the user do that by hand, we'll say, we'll take the program, and for each of these race reports, we'll randomly run the program, but not just a naive random scheduler. We'll bias the random schedule in a way that will make it very likely for this particular race to occur if it's feasible. And then what we'll do is we'll only report the data race to a user if we see it in a real run. And of course, we might be giving up here. Maybe some of those reports were real and we weren't able to create them. So the user can go through and look at them if they want. But we'll find in practice, for the data races that or atomicity violations or deadlocks that are possible, this technique tends to find them very quickly. And it's much more useful to give the user a real bug in a real execution than just this report of a possible bug. So this technique is called active random testing, right? And we've implemented it in a couple of different tools. So CalFuzzer is our tool for Java, and it's it's open source. You can download it from our website, and it's designed to be very extensible. So if you want to write your own predictive analysis or your own random scheduler, it's pretty easy to kind of plug into our infrastructure for capturing all the reads and writes and synchronization events in a program. And it works for a variety of different kinds of bugs, for data races, atomicity violations, and deadlocks. So also for C and P threads, we have a tool called Thrill. Right now, it just works for data races, though we're working on adding more capabilities to it. And it has some other features for kind of simplifying buggy executions to make them easier to debug, which I'm not going to have time to talk about today. And also another kind of exciting development, right, so you just had a talk about UPC. We're also developing a version of Thrill that will work for Unified Parallel C. And actually, we're hoping it will be part of Berkeley's UPC distribution by the end of the year. Mm-hmm.
Is Thrill downloadable?
Yes, it is. And actually, when I put the version of these slides online, I'll include URLs, because it's a little hard to find that code. Yeah. I did say we have, I'll talk about this a little more later, but we have applied both CalFuzzer and Thrill to a number of programs. Although, at the moment, they are still kind of academic code, so that they can be a little bit hard to get running. But they are both very extensible and really designed, so they have a lot of power, and you can really add to them if you want. Okay. Right, and in particular, so this overall tool is called CalFuzzer, but this particular technique, just for doing this for data races, is called RaceFuzzer. And just to really show how this all works, I'm going to show a couple of examples of RaceFuzzer's operation. So consider kind of a simple program here, well, a relatively simple program. So it's code. It has these two functions, the synchronize method foo, which you should think of these functions kind of maybe G1 through G4 as doing a lot of work, but kind of it's safe local work. And then having this write to a field at the end. And then also this method bar, and maybe there's a race between this statement at line 5 and this statement at line 6. And then, we have several threads calling kind of foo and bar in parallel on different objects. Okay. So the first step, right, we'd run our predictive analysis. And let's say that analysis told us, there might be a race between statements S5 and S6. Right. So now the key to our active testing algorithm here, right, so there's the potential race. So the goal, we want to create a trace that really exhibits this race. For example, something like this. And this is a trace where, threads 1 and 2 run for a while, or threads 1 and 3 run for a while. And then these statements S5 and S6 we have instances of them, dynamic instances that run right next to each other, and one of them is writing to the field f of object 01, while one is reading from field f of object 01. Right, so this would be a trace that actually shows the error. So we'd like to see, can we produce something like that? Okay. All right, so instead this is going to be a random scheduler. So at first we're just going to start, at each time step we'll randomly pick one of the threads and we'll advance it by one step. Right, and we do this all by instrumenting Java bytecode so we can kind of take control of the execution of a program. Okay, so we'll use our random number generator here and say it picks thread 1. So we'll run one step of that. Now again, we'll randomly run another thread. We'll say we'll run thread 3 here. And we'll do that for a while until we hit one of the statements that's in this racing pair that we're trying to create. So the statement S6 from thread 2. Okay. So that's in our racing pair. So now what we're going to say is, rather than just continuing to randomly schedule the execution, we want to pause thread 2. Right, we'd like to hold off and let the other threads run and see, does any of them encounter a statement that races with this statement. So we'll say, okay, we're pausing the execution of thread 2. We're not going to let that statement run. And instead, we're going to continue executing the rest of the program. And of course, there are some tricks we have to do. We might accidentally kind of postpone every thread in the program, and then we'll have to kind of detect that we've done that and rerun, and let one of them go forward. Right. Okay, so now we'll continue running this program. So we run threads 3 and 2 for a while until we encounter another statement that's in this racing pair. In this pair of statements that we predicted might be in a race. So here we'll say, okay, statement S5, that's in the racing pair. And so we'll check, is it actually a race with any of the other threads we've postponed? But in this case, it's not a race, because one of them is a read from field f of object 01, and the other one is writing to a field of object 02. So although they're matching statements, they're on different memory locations. So we haven't found a race yet. So instead, we'll also postpone the execution of thread 3. And then we'll continue executing, and there's only one thread left. So we'll run thread 2. We'll run thread 1. Okay. So it'll advance until either it finishes or it hits a statement in this racing pair. So it reaches statement S5. And now again, we check, is this in a real race with any of the statements that we've postponed? And in this case, it is. All right, so we've actually constructed an execution here where we have a write to this memory location and a read of this memory location, and either of them can run right now. Okay, so we can report we really found the race. And even further, we want to continue the execution. We might as well see if now we hit some kind of program error, right? If we crash or if we print the wrong thing. So we'll randomly decide, we'll let one of them go first, and then we'll run the other one right after it. Right, and in particular, in this case, we have a 50% chance of running thread 1 first, and then we'll see this error. We'll write one to the field, and then we'll read one from it in this real race, and for this particular program, that happens to trigger an error. Okay, is that clear? Mm-hmm.
Question, what happens if they have an off by one error, and the first 20, you're going around a loop, the first loop, the first 20 executions of the statement are fine, at the 21st match
Right.
against the first of the next one, and if you postpone execution on the first element, you'll never get to the 21st element, which causes the problem.
Right. It's a great question. So just to repeat it, I'll say, what if, here we've said we pause as soon as we see any statement that's in our racing pair. But what if that's kind of the wrong thing to do? What if the first statement we pause, that's not really in a race, but by pausing there, it prevents us from seeing a later race? So in fact, to deal with that, what we do is we actually only pause each thread with some probability. And in some sense, as we, that probability starts pretty high, but as we see the statement over and over again with kind of the same memory location, or if we see that on multiple runs, we'll decrease that probability so that we kind of explore further into the program. Mm-hmm.
Do you have the concept of neighborhood here? I mean, if you see pieces of code which are actually run regularly separated by 10 minutes, would you still holds the file. Do you see what I mean?
Oh, yeah, yeah. Yeah, so I guess there's one question about, you know, maybe is this exploring executions that are, you know, very strange, something like, you know, we look at two pieces of code and we say they could race, but in fact in any real execution, you know, they run 10 minutes apart in time. So I guess there's sort of two answers. So one is that some of the errors we find are things where, because of kind of, the errors that happen when one thread is paused really for a long time. And so some initialization it does kind of doesn't happen before other threads need it. So it's true that in normal circumstances, those kind of races are pretty rare. Although, of course, if you're in cases where maybe the machine is kind of oversubscribed and you weren't, you know, kind of, and you weren't expecting that, you can sometimes see behavior like that. But yeah, there is also some question. Actually, in the real tool, we also have a little bit of, we have some timeouts. So we don't actually postpone any statement for more than, I forget exactly what they are, but you know, maybe a few milliseconds or a second or so. Yeah, to prevent, you know, getting races that are so strange and unlikely that the user's just not going to care about them. Great. Okay. So here, this was round one execution. I just want to show another quick example here of RaceFuzzer. And the key here is I want to show. Right. So this code has a race. Actually, this is somewhat like the one you said, where, you know, here thread one kind of runs a bunch of code, and then it has this read of X kind of right at the end of its work. And thread 2 has this write to X kind of right at the beginning of the work. So you could think maybe this write at line 10 is kind of an initialization. And on most runs, so you could do kind of a normal run, or if you kind of naively randomly execute the program, kind of at each time step you just pick one thread to go forward randomly, it will be very rare that you see this bug, right? Because you know, if thread 2 ever kind of starts running before you get to the end of thread 1, you won't see the bug. But this is really a problem, and we might want to know, you might still want to see that this error is here, you know, especially if when it turns out that if you switch to some hardware, maybe now when you run on your advisor's machine, that maybe you can really trigger this race now. It would still be nice to eliminate it. And the one thing I want to show is that although this would be very hard to create with kind of a naive random scheduling, in fact, RaceFuzzer will create this race with a very high probability. So we'll very quickly find it and report it to the user. All right, and the reason for that is, you know, kind of right at the beginning, as soon as we encounter this x equals 1, you know, with a pretty high probability, we'll put it in the postpone set, and then we'll just run all of thread 1 until we get to the end. So, you know, we can see that because it's really relevant that we try to run lines 8 and line 10 at the same time, you know, we can delay a thread, you know, kind of for a long time as long as you don't hit some timeout. And in fact, we'll create this race with something like, you know, roughly 1/2 probability, where this would be very hard to find otherwise. So it's just, okay, so I'll just talk a little bit about how this tool is implemented. Right, so this RaceFuzzer algorithm, it's implemented as part of our CalFuzzer tool suite, and also as part of you know, our Thrill tool, and soon our UPC Thrill tool. And for Java, the way this works is actually we do bytecode instrumentation using this tool called Suit. So after you compile the code, our tool will go in, and whenever there's a read and write of a field, you know, we'll insert a little method call to our analysis library that'll say, you know, hey, this thread just wrote to this field or read from this field. And we'll do the same thing at locks, you know, forks and joins, kind of any synchronization events. And then this instrumentation we can also use to kind of take control of the scheduler. So when some thread is about to write to a field, first it calls into the analysis library, you know, telling the analysis library this write is about to happen, and the library at that point can just pause and it can block the thread. And that's kind of the mechanism for postponing and for creating the schedules we want to see. And, you know, to make sure we have good control over what's happening, we actually only run one thread at a time when we're doing this active random testing. And again, because there's some pieces of code we can't get to, so inside native code, it's actually still possible to acquire Java locks. So we won't see things like that. So we do have to periodically check if we've just blocked all the threads, and then we'll wake one up to let our testing make progress. Just an example, you know, here, if this is a program here, right again, we'll insert all these calls to say, you know, instrument a lock acquire, instrument a write, instrument a unlock, and those all go into our custom scheduler. Okay, so I'm not going to go into these in detail, but I'll just say we've run the CalFuzzer tool over a lot of Java code. These are ranging from, you know, some Because things like Moldine and Ray Tracer, Monte Carlo are kind of small parallel computing benchmarks. And also some kind of fairly decently sized Java servers, like this, I forget exactly actually what Jigsaw does, but Jigsaw is a simple web server, I think. And you can see we're able to really run on these, and you can kind of get a sense here of how many race reports you get if you use a hybrid race detector. And that's in this column, number of races hybrid. And you can see that by using active testing, we're able to narrow that down to just the handful of real races that exist in the program. Although actually for this Jigsaw web server, the number of real races was quite high. And when we ran these tests, most of these races were not previously known. So, it was just kind of a couple hours to test each program, and we found a lot of races that were really out there in the wild that we could report to the developers of these tools. And we've had similar results when testing for atomicity violations and testing for deadlocks. And also some even kind of more esoteric kind of errors like determinism or non-determinism errors and memory consistency errors. Okay, so just kind of to summarize here. Right, so active testing, we combine a lot of the useful features from this predictive analysis and this random testing. So we're able to get good coverage by looking at all the races that this kind of predictive analysis finds. And in fact, we can use a predictive analysis that has very good coverage and lots of false positives because we don't really mind if they're false reports. It makes our testing take a little bit longer, but then we filter out all the false warnings. And we also have a fairly inexpensive way to replay a parallel execution when we find a bug. Because again, we have a pretty good control of the Java scheduler. If you run our biased random testing twice with the same random seed, you usually will get the same execution. So the user can see the bug kind of over and over to help debug it. And we also have some ability to, here there's separating kind of false alarms from real data races or real atomicity violations. And then we also can help a little bit with the question of, separating, is this data race, does it really lead to a program error? And can it cause incorrect output? Or is the data race benign in some sense? Because there are, in certain kinds of code, you sometimes put in intentional data races for performance reasons. And so we'd like to be able to tell the user at least, well, we found 10 real races, but the ones you should really focus on are the 3 that we found led to crashes. And this whole process is kind of embarrassingly parallel because each different race report or each different kind of biased random execution, we can run those all in parallel. But again, right, there are still limitations here. So like any testing tool, this isn't complete. Right, so we get pretty good coverage, but there are easily still parts of the program space we miss, and so bugs we won't find. And of course, we also can't separate all the real races from the false warnings. Some of the warnings might be real, but it's just too hard for us to create the random schedule. So then the user still has to decide do they want to look at all the false reports or just know that they might still miss some real bugs. Although in practice, we found that when we've run on benchmarks that had known bugs, we've been very successful in finding all the ones that were known in addition to finding some new ones. So in practice, coverage seems to be pretty good. And again, also, we of course can't perfectly separate races that can really lead to, crashes or incorrect output, because again, we can't explore all the program executions after creating a race. Right, and of course, there's some overhead, both from making all these instrumentation calls. Right, so there's a call into our library for every read and write the program does. This is actually true of all predictive tools and a lot of random testing tools too. But it does mean these dynamic analyses often have an overhead of kind of 10 to 100x, depending on the program. So you have to run them on pretty small problem instances. And we also sequentialize the program during our testing. So if you really want to run it with thousands of threads, that might be a problem during testing. Okay. So again, I just say this is a way to kind of combine the benefits of random testing and predictive analysis. It's something we've been working on in the Parlab for the last few years, and it'll apply to a lot of different kinds of bugs. And it's available right now. You can download the tool CalFuzzer for Java and Thrill for C and P threads. And we also have this tool UPC Thrill. We're collaborating with people at the Berkeley lab that we hope will be part of this UPC distribution by the end of the year. Okay. So just to wrap up. Right, so again, I hope one thing you took away, there's been a lot of work on developing these techniques and tools to find a variety of these kind of parallel bugs that it's quite easy to make in programs. And a lot of these tools are available now, from our tools, Intel Thread Checker, tools from Microsoft, from IBM. And it can sometimes be a little hard to get these tools working on your program, but when you do, they can be very effective. They can really help improve the quality of parallel software. But the other point is, of course, this is no silver bullet. I think one theme you'll see in the next talk, you still have to very carefully design your parallel application. And as you're writing it, you really have to know kind of what data is shared and how is it shared. How are you protecting or partitioning your data? So these tools are really great for finding mistakes. When you had a careful discipline, but you didn't always follow it, because that can be hard to be very careful about it. And in that case, they work really well. But if you're doing some kind of ad hoc parallelization, just kind of starting by running things in parallel and then not thinking too much about what might happen, and then just kind of trying to hunt down bug after bug until you get the program right, that process is not likely to ever work, just like in the sequential world. You do need to do a lot of this thinking up front about, how to make sure you don't have these races, deadlocks, and atomicity violations in the first place. All right. So, thanks very much. And are there any questions?
Intercepting. Oh yeah. I'm not quite sure how this kind of intercepting the scheduler and whatnot, works with a language like C, in which you don't have a virtual machine behind it. How is it done? So for what was it called? RaceFuzzer, the last tool you have. Would this be possible to do with in C, for example?
Yeah. In fact, this may sound a little strange. It's actually a little easier to take control of the scheduling in C. Because in Java, you have this problem of native code, which if you can only instrument Java source code, you can't tell what that native code is doing. So it can kind of do a runaround around your own scheduling. But in C, you can actually replace the pthreads library with kind of a version of the pthreads library that we control. And in fact, there you're pretty sure to capture everything the program's doing. And in fact, we often use binary instrumentation to make sure you really get every read and write kind of performed by the machine code of the program, and every call into parallel libraries. So in some sense, we actually have better control of C programs than Java programs.
So the C tool that you mentioned should seamlessly work for OpenMP, right? Or it's only for pthreads?
Yeah, no, I believe so. So it's for things like OpenMP and TBB, which underneath are just using pthreads. Then we can do the same technique of kind of replacing the pthreads library they use with our own, and again capturing and taking control of the scheduler there. Yes.
Thanks.
Great. All right, thanks. And I'll be around afterwards if there are any more questions people want to ask in person.